Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
In the second example, we're after the same values as earlier. We would like to know the impulse and average force when a ball is being kicked. And as we can see, the ball takes off at an angle of 45 degrees. So the force must be inclined some angle from the horizontal as well. We'll use the vector formulation to solve this problem. And we have the coordinate axes here already, so we don't have to define a specific positive direction or directions. But we can state right away that the vector 1 or the velocity 1, it's to the left, so it has to be minus 20 meters per second, and I indicating x direction. And then the v2, the final velocity, it's going at an angle of 45. So it has two components. So if this is v2, this is v2x, and that's, if that is, let's call it alpha, we can say 45 degrees. It's going to be sine 45 times the magnitude of v2, and then the vertical component is then v2 times sine of 45 degrees. Oh, if that's, yeah, that's sine, so this is of course cosine, because it's adjacent. Right, so now we can write for v2, the magnitude v2 times cosine 45 degrees in x direction plus v2 sine 45 to the j direction. And so v2 times, or we can write explicitly already, v2 is 30 meters per second times cosine of 45 is, that's 1 over square root of 2 I plus v2 again, and the sine of 45 is also 1 over square root of 2, but this is in j direction. These are both 21.2 meters per second. Like this. And now we can evaluate the impulse imparted by the kicker. So that's just the difference or change in momentum. So it has to be P2 minus P1, and P2 is m times V2 and P1 is m times V1. So we get mass times the difference of these two velocities, v2 minus v1. And what do we get? In I direction, we have first of all v2, 21.2 meters per second. And what is the I component? That's v1, so minus, and then the actual value minus. That's important. Like this. And in j direction, we have v2 component minus whatever is the j component of v1, and there is none, so that's going to be 0. So we get mass of the ball, which is 0.4 kg, that wasn't explicitly written out, but let's put it there. Times, in I direction, we have 41.2 meters per second, and in J direction, 21.2 meters per second. This is the vector form of the impulse from the foot. And we can now evaluate the magnitude. So basically just using Pythagorean theorem, because it's a vector, so both components to the second power, and they also have this mass in front of them both, so that's going to be also there, common for them both. So, and then the I component, for example, 41.2 meters per second squared, plus the Y component, 21.2 meters per second squared, and that's the square root of them both, of them all, and we get 18.53 kilograms times meter second. So that is the magnitude of the impulse. That was pretty much part A. And then B, what is the average force? Well, average force is, again, J divided by, or the impulse divided by the time it takes. So 18.53 kg ms divided by elapsed time, 0.01 seconds. So we get about 1.9 times 10 to the 3 Newton seconds. Oh, sorry. That's of course seconds squared, so it's going to be newtons because it's a force. So that's the magnitude. What about the direction of the force? Let's use this space. We have some more room here. So we calculate the impulse in a vector form, and the impulse and the force are always in the same direction, so we can just evaluate the direction of the impulse. We had impulse in the J direction, or I mean X direction, and in the Y direction, so then we are able to calculate the direction of the actual impulse from this angle alpha. So we get tangent alpha is jy divided by jx, and hence alpha is the inverse tangent of that ratio. Let's put the values in. So inverse tangent of J component, that is the Y component, so it's 21.2 meters per second times 0.4 kg. Divided by the X component, so that's 0.4 times 41.2. And these all, of course, cancel. And we get from the calculator approximately 27 degrees. Notice that the force was in different direction than the velocity. And this is because it is the change of velocity what matters. In X direction we have change of total 41.2 meters per second, and in the Y direction only about half of that. Hence the angle of the force is well below the 45.
always